All good? All right. Hey, everybody. It is 7:15, and I would like to call to order the November meeting of the Madison Astronomical Society. If I could have everybody's attention, please, we'll have a few announcements and things. And maybe a surprise or not, I don't know. Yes, I'm Lawrence Moore. I'm the president of the Madison Astronomical Society, and it's so great to see everyone here tonight. Before we introduce and get started with our guest presentation tonight, there's a few announcements, and then maybe if there's some, later on, if there's some people who are visiting us for the first time, we'll get to know you a little bit. If you would like to introduce yourselves, that'll be coming up later. The first announcement is we do have our ongoing renewal drive. I don't know, yeah, so if back in September we sent out our renewal notices, and those, everyone should have received them in the mail. If you haven't received anything in the mail, talk to Jürgen right there. And just to let you know that one of the greatest benefits of being a member of the society is it's just such a great opportunity to meet people with similar interests and be able to enjoy a little stargazing together. And then when you come here on monthly meetings, just like tonight, we've got a really great presentation. It's almost like you're going to an episode of Nova, except it's like in a nightclub or something where and you can actually ask the expert a question or two. So it's just totally great. So, and then also, in case you haven't noticed this year, there's a new thing where you can join the Astronomical League, which is a really neat national organization geared towards amateur astronomers. And if you're like new to the hobby and like, say, like myself, I have no idea which constellation is what in the sky, they have programs to help you learn that. They have programs to help you learn how to observe. It's a really great program. So that is a little extra on top of our annual $60 fee. For a little bit of extra, you can join the Astronomical League for the remainder of this Astronomical League's fiscal year, which is in July, I believe, is when their fiscal year begins. And then you also have a membership for their fiscal year following that. So that's another new benefit. And then, of course, one of the best benefits, of course, is if you got a telescope, or if you just like this, you're just looking for a place to get away from Madison's light pollution and you want to get out of town and have a nice place to be able to observe, we have our own property that we own, and it's called the Honor Research Station, and every member of the club is entitled to observe there. So if you haven't sent in your annual dues, please do so as soon as you can. And please note, yeah, we do not, unfortunately, have a digital payment system. All right. So, any questions? Anybody have any questions on that? Hearing none, I will move on to some future events that are coming up. We have next month on Friday the 13th. Dun, dun, dun. We have our next monthly meeting right here at Space Place. It's going to be an MES holiday party, and we're going to have a clinic on electronically assisted astronomy. And so some of the people that are here tonight will be giving us the lowdown on all the neat gadgets, and you'll be amazed at how affordable some of these gadgets are. All the neat gadgets that are available on the market to be able to, in case you're looking through a telescope and you can't see things real well, especially like myself as you get a little bit older. We have all these new electronic gadgets like the C-Star that'll turn your smart pad or your smartphone into a hyped up, juiced up eyepiece. So be there for that. And also for the holiday party, we usually invite people, hey, if you want to bring a little snack, a little beverage or something, non-alcoholic beverage, let's have some snacks and enjoy the presentation. So that's coming up on Friday, December the 13th, right here. Does anybody have any additional announcements they want to make about that program? Oh, yes?
No, not about that, about
okay.
something else.
All right, I'll get to you in a minute. Also, coming up, and we want everyone, I just want to reiterate, we want everyone to save the date for Saturday, April the 5th in 2025. 5 p.m. we're going to have our 90th anniversary gala celebration at hosted by the very generous Promega Corporation. They have a banquet facility lined up for us, and it's right next to the Bell Burnell Observatory, which was formerly the Oscar Mayer Observatory, which was formerly the home of our very club and our former Dark Sky site. So it's going to be a really fun time with lots of good food and lots of good company. So get it on your calendars right now, Saturday, April the 5th. For those of us who say, you know what, tonight's presentation isn't enough for me, I want to see another real neat presentation this week. Come back here on Tuesday, November the 12th at 7 p.m. There will be a presentation called Aging Worlds, Tracing the Evolution of Planetary Systems by Professor Melinda Soares Furtado. And here's the synopsis. How do planetary systems evolve over time from their youthful beginnings to their eventual decline? Using several star-planet systems as case studies, we'll dive into the processes that lead to planet-star interactions in aging systems. These systems will help illustrate broader insights into the composition, formation, and the ultimate fate of these worlds. Ongoing studies from the Hubble Space Telescope and the James Webb Space Telescope are shedding new light on these subjects. So come right back here Tuesday night. And
is that being sponsored by?
That's being sponsored by UW Space Place, and they have their own monthly guest presentations on the second Tuesday of every month. If you're looking for an excuse to go to the Madison Metropolitan School District Planetarium this month, on Wednesday, September the 20th and Thursday, November the 21st, they're having a holiday-themed show called The Magic Globe, A Story of the Seasons. And it's about apparently about a girl who goes to the grandfather's house, and this grandfather's house has this mysterious piece of some sort of neat astronomical telescope or something, and it's all about this, kind of neat magical thing. So anyways, that's coming up for Madison residents. It's $6 per person and $9 for non-residents, and tickets can be purchased online, or if you want to roll the dice, if they've got seats left over, you can buy tickets in person. All right, so I know Jürgen wanted to say something about a special offer for the season's greetings.
It's only appropriate that the person who handles the money is trying to sell things. We have two things, and I already announced one of them through an email, and I got a couple of responses. We've been doing for, I don't know, I think Chris started with the calendars a long time ago, and we've been selling calendars.
You want to?
Testing?
Yeah.
Testing good. These are the calendars published by Astronomy magazine, and normally by this time I have them. We ran into a bit of a snafu, because Kalmbach Media, which owns Astronomy magazine and a whole bunch of railroad-related and other hobby magazines, sold all the magazines but one to a company in, I think, Tennessee. So I used to be able to drive down to Milwaukee, pick up the calendars, and bring them back. However, now they have to be shipped, and they'll be here early next week. So I can't show you the calendars. But we do sell them. They're cheaper than if you buy them in a store. There's a little bit of a fundraiser for the club in them. But if you want them, let me know, and I put together a list, and I'll be delivering them when the calendars come in. I'll also have them for sale, actually, in the December meeting, Friday the 13th, right? Yeah.
That's right.
The other thing is, and John, of course, reminded me of this, because I'd forgotten about it. For those of you who are interested in the history of the club, which should be everybody, we have this marvelous publication, The History of the Madison Astronomical Society, 1935 to 1988. John Rummel and Dan Strom, Dan did some of the research for it, put this together. We charge $10 for it, which is it's the cost of publication. History of organizations often is really the history of the people who created it, and that's what's great about this. There are a lot of stories about people. If you've been around a while, you've already seen this, but they are available, actually in the back room. So if you're interested in buying them, you can see me or just send me an email and we can get them to you. And of course, if you're new to the club, or if you're here and want to join the club, I do have forms, membership forms. If you want one, let me know and I'll hand you one. And if you actually have the money, I'll even take the money at this time. Happily. So, thank you.
These are like kind of big picture questions that motivate a lot of things, is trying to figure out what's out there, I guess. And so one kind of example of this is like trying to figure out what's out there is something called the supernova, which is an explosion of pulled onto the mass of the other star. And but these two things are interesting in itself, but they also are interesting because in stars, as you might know, you have fusion. So you have like two hydrogen atoms that are coming together to make helium, and then from helium you move on until basically you get to iron, and then you have your explosion. And so what happens is, with the explosion, all this material is getting ejected and going outwards into the rest of the universe. And then you have new stars forming with this new ejecta, and so on and so forth. So early stars have very little iron or heavier elements. They're mostly hydrogen and helium. But later stars now, since you have younger stars that have already exploded, have this iron in it itself. So you can kind of do like a time catalog of when a star exploded and how old it is. And this is interesting because, again, we're trying to catalog the universe, trying to figure out what's out there, and we want to know what kind of elements are out there. So if we're looking at a star and we see not a lot of iron, we'll know it's pretty old star. If we see a lot of iron or other heavy elements, we'll know that's kind of like a young star. And that kind of brings us to this idea of like trying to figure out what things are made of, particularly what elements they're made of, because we can say, oh, we know the elements, we know what kind of star it was from, we know all these other things. So it kind of leads me to this quote I put on there that everyone likes to say that we're all made of stardust, and that's pretty true because you don't get any of the heavy elements that would collapse, like he says, in calcium in our teeth, iron in our blood, carbon in our apple pies. All that is created during fusion and thereafter the explosion of a star. So trying to figure out all these things and what they're made of is kind of like the base goal of astronomy. And it's tricky because in other sciences, you can do an experiment in the lab and you can say, okay, this rock or whatever is made of this percent of this element, this percent of this one. But we can't really do that. We can't really go to these stars and say, oh, let's take a sample and figure this out. We kind of have to be maybe a little more clever or think about how we can actually do that. And that's kind of where the idea of like how do you make different instruments, different telescopes, so you can actually figure these things out when they're millions of light years away. So that kind of brings me to this topic. The main thing in astronomy, as you know, when you're looking through your telescopes, you're looking at light from far away. So we call that a messenger. So light is the primary, or photons are the primary messenger in astronomy that basically dictates all of the field, but there's also things called neutrinos and gravitational waves. Those are two separate things that also can give you a lot of information. I won't really be talking about them though, but talk about light, which is the electromagnetic spectrum, which is this image on the left, or on the right. And so I think most people are pretty familiar with the visible light. That's kind of what you see with your eyes. So you look out in a telescope with your eye, or you just look outside, or you're looking right now, you're looking through your eye and you're seeing visible light, like red through blue. But there's a bunch of other types of light that are actually really important also in astronomy. So things like radio waves, which you might think of when you're listening to the radio, that's also electromagnetic waves, and they also come from space. And X-rays, which is what I focus on, you might think of when you're going to see a doctor and you have a broken bone, but you also get a lot of X-rays from space. So using all different wavelengths can give you a lot more information than just looking at visible, which is typically what we think of. For example, different wavelengths have are from different or produced from different processes. So you can get an X-ray and you know, oh, this physical process happened at this star. That's why it produced an X-ray. But you won't have any signal in the visible light. So you have to be able to understand the physics about that, and then also be able to make observations in these different wavelengths. And they require different types of instruments and different energy ranges. And so that brings me to like the last part that I'll start talking about is like there's two kind of main ways to collect information when you're using telescopes, more or less. There's imaging, which is basically what you think of. You take a picture with a camera and you get an image of it. And then there's spectra, which is maybe not as commonly known. It's when you kind of know, you don't really get an image of it, but you learn exactly what elements make up a certain pixel, more or less. So, and that's really powerful. Imaging might seem like the main thing in astronomy, but most astronomers actually really care about the spectra, because that's what tells you, again, what exact elements you're seeing in your picture. You do care about what the actual picture looks like, but you care more about exactly what elements are making up it. That's what you get from a spectra. So to kind of go back to this idea of you have different wavelengths, this is like a picture or a movie that I'll show of the Eagle Nebula. And so I think it's a pretty famous picture of the pillars of creation. And most people, you probably see it in visible light, but again, you can take pictures in different wavelengths and then the picture looks very different. So this first part, you can see in the bottom right, it says what it is, but the first part is this image is optical, so it's kind of the typical picture. This is X-ray, it looks very different. You don't get any of the light column thing. This is in infrared or near infrared. This is in far infrared. And then this is a different optical telescope. So you can see how each picture is kind of different. You're getting different information from each of them. Okay, so then to kind of go back to that, the left is X-ray and the right is optical. You can see just how different the two pictures look. Like the optical data, you can see the actual pillars, which are dust and parts of where star formation is happening. But that you don't see in X-rays because the X-rays don't really interact with the dust in the same way the optical light would, just because of the different energies and the different scales. So you get two different images and you get a lot of different information. So it's important to use both of them and try to get the combination. So then here's like the combination of the two pictures. You're adding them together. And so something I'll talk about now also is that you might think about when you're thinking about X-rays, also it's not something you see with your eye. So if you're going to get an X-ray on your arm, you're not going to actually see the X-ray light with your eyes. Our eyes are only sensitive to the visible light section. So when you're making pictures like this, you might have heard people say like false color, which is what they're doing, even kind of with optical images a little bit, is that you kind of have to choose the color that each energy range is going to be in the picture, and then you make a picture of that to be representative. So you're mapping an X-ray energy to an optical color, like green or whatever, and then you put that on the picture. Otherwise, we wouldn't be able to see anything in the image. So that kind of brings me to the same picture now. This is what James Webb Telescope, James Webb Space Telescope. And so the way you actually make these kind of picture is the same way your eye does it and the same way a camera does it, is that you don't just like take a picture. You take a picture or take an image with several different filters. So the bottom are all the James Webb filters, and each color, the color of the actual name of the filter is the actual color of the filter, more or less, and the color it is in the image. And so you take an image with each filter on, and then you combine that together to stack it, and then you get this image that would be representative of what you would see with your eye, because I think this is more or less an optical image. And so the same thing happens when you're taking a picture with your camera. You're not just taking a picture, you're taking a picture with a red filter, a green filter, a blue filter, and I guess color theory, you combine them, you can basically create any color with the three different filters. So that's what we're doing here. Each filter is sectioning out a specific wavelength. So like, I guess, here you can see that if you have this one filter here, you're only getting light from this one filter, this one energy range or this one color range. And then you put it on top of with the other filters and then you get this really nice image. So everything kind of is this false color thing, but it's the same thing that your eye is doing also. And then you also do that when you have things like X-rays and gamma rays or whatever, but those are a little more arbitrary in what color is what filter, because there's no exact equivalent to your eye, but here it's pretty easy because it's an optical image. But here I'm just reiterating this point that there's called the small, medium, and large parts of your eye. I forget their name, but you also, rods and cones. And so you have more of a blue section or green section and a red section that are interacting all at the same time, and that's how you get all the different colors that you actually see. So it's kind of the same way that the filters on these telescopes are doing that. And so now to this idea of a spectrum, and how do we actually know what element is what light, and so on and so forth. And so this here is an image of a hydrogen atom. Hydrogen atom has one proton and one electron. And so what's really important for astronomy, and it makes the difference, is that electron moving from any of these energy levels in a hydrogen atom is unique. So if it moves from the first level or the second level to the first level, it'll emit light, but it'll emit a very unique wavelength of light. If it goes from level 3 to level 1, it'll emit totally different wavelengths of light. So you know from lab experiments exactly which levels correspond to which energy, or which photon energy. So you're looking at space and you see this very specific energy line, you know that's a hydrogen atom that had a electron drop from the level 2 to level 1. So that's how when we're looking into space and we see whatever signal that we see, we can say that's hydrogen or that's iron or whatever, because we've done enough experiments in the lab to know exactly which elements and which compounds and molecules emit light at these very specific energies. And so this is how we can do this kind of spectrum thing that I'll say is more powerful than just an image alone, because you can do this thing where you know what elements different energies are coming from, and then you can say what's making up your image with different elements. And so this is a picture from James Webb. The top is an image, and then the bottom is if you choose kind of like one pixel in this large image and you were to use a detector that can make a spectrum, which I'll talk about after, then you get this graph at the bottom, which is on the x-axis is the wavelength of the light, which corresponds to also the energy, and then you have how basically intense it is. So you can see they haven't exactly characterized it, but there's different types of hydrogen lines. So you can see it's saying this peak here, we know the energy of hydrogen produces a line right here, and it's very unique. It's not a different element. And this line is very unique to oxygen. So we're saying, okay, this pixel has all these different elements and these different abundances. We can learn all these things about it. And so another interesting thing that you can do with this spectra that's really important in astronomy is measuring distances. So you can get the elements, which is really important and really useful, but you can also get distances. And distances in astronomy is one of the hardest things to do, and it's also really important. Distance is really hard. Again, you can't just go out and measure things with a ruler. You have to use different techniques to figure out how far something is. And that's something important for cosmology and knowing the size of the universe and how far things are away from you and so on. And so it's kind of based on this principle called the Doppler effect. And so you might recognize it in your own life when you hear like an ambulance. If the ambulance is coming towards you, it's higher pitched, and if it's going away from you, it's lower pitched. And so this kind of same thing happens with light. If light is moving towards you, if the object emitting the light is moving towards you, it gets blue shifted. If it's moving away from you, it gets red shifted. which means if the object is moving towards you, if the light is whatever color, by the time it gets to you, it'll be even bluer. So it'll change the color of the light, basically. And so this is important for astronomy for a big picture because the universe itself, everything that's not gravitationally bound to us, kind of more or less, is moving away from us at an accelerating rate. So things that are far away from us are moving away from us. And so we can measure how fast they're moving away from us by knowing their spectra. So if I know their spectra at hydrogen is always at this one wavelength, and now it's shifted however much, I can then use that measurement to know how far it is away from me and how fast it's moving. So we can use this technique to find how far things are away from us, to know when people say, oh, we're finding galaxies that are whatever 13 billion years ago, they're using this technique to say that's how far away they are, and that means that they're this old. So again, you need a spectrum to do this. You can't just look at an image and say how far something is away from you without some other techniques, I guess. And so that kind of brings me to how do we actually now measure all of these things. One type of very common detector that you can use in a bunch of different energy ranges is called a CCD. It's the same detector that is in your cell phone camera and on almost all probably digital cameras also. This is a picture of it on the right from the Vera Rubin Observatory, which is being, I think it's mostly built now and just being commissioned, not exactly sure, but it's should be live in the next couple of years. But it's a very large telescope, and they also use CCDs. And so the way that kind of a CCD works, as I was talking, it needs filters to do any kind of color imaging, and so like I can do some spectrum, but that's a different technique. But the way the CCD works is actually you have a grid of pixels, and you can imagine the pixels are just buckets, and you're pouring water into the buckets, and however much water you're pouring into the bucket kind of relates to the intensity of the light, or intensity of the rain that's falling into that bucket. And so you're eventually doing like a little bucket brigade where you're moving the buckets over. Eventually you pour the bucket over the edge, and you can measure how much water was in the bucket, and then you know how much rain fell into that bucket during that time period. And so more or less that's how much, the analogy, that's how much light, intensity of the light hitting that pixel at that time. You're reading that out as the number of electrons later on, and then you get your image from that based on the intensity of light. And then when you also couple that with the filters that I talked about earlier, you get your color image from your camera on your cell phone or from on a telescope. And so, as I kind of said, I guess CCDs are really, really powerful devices, but alone they can't do this spectrum thing, but they can take really good imaging. If you do a CCD with something called, basically something like a prism, you could maybe do that, or people do that a lot, but I won't talk about that in this talk. I'll talk about the devices basically that I use in my lab, or that I'm trying to design in my lab, and they're kind of more of a thermal detector, so they work on kind of a different principle. These detectors are basically a thermometer, and you can think of this picture on the right is kind of how the detector works. Is that light comes in, it heats up this surrounding material, which in this case is the water, and then your detector as a thermometer measures its temperature change. And you can kind of think of the light heating up the water as like you go outside into the sun and you're sitting in the sun and you're warming up. The energy, the photons from the light are thermalizing on your skin and you're heating up. So the same thing happens in this example of water. The photon hits the water and it turns the photon from the photon into thermal energy, and you measure that thermal energy as a change in temperature. And so for us, that means, back to this idea, is that you have this temperature change that you're measuring with your thermometer or detector. That corresponds to the actual energy of the light, because the light is turning into thermal energy and heating up the water. If you know the energy of the light, you know the color of the light, and then we do this whole thing where we then get the material of the light because we know the exact energy and color that correspond to each element and each elemental transition from the lab. So we can do this game to actually get our spectrum that way. And so these are some pictures from stuff that I actually do. So, and particularly X-rays. You can do CCDs with X-rays, but we could also tend to do our thermal detector. The detectors I work on are called a transition edge sensor. See the picture on the top right? So they're really tiny. CCDs are also tiny. This detector here is like 50 microns wide, which is about the width of your hair. And then this bottom picture on the right is of an entire wafer that we call, that's like 4 inches across. I actually brought an old one that I can hand it around if people want to look at it, I guess. So that's kind of this bottom right picture, and has like a bunch of our detectors on it. And so we do this, one thing that we do to make these is that we do this in a clean room at the UW-Madison campus. And to make all this really clean, we don't want any contamination or dirt or anything. Mostly contamination from the people actually using it or using the facilities. But this is a nice kind of figure or fact that I think is pretty interesting. So in the clean room, you get around 100 particles per cubic foot, and then in a room like this, you have 500,000 to 1 million particles per square foot. So it's really pretty clean, temperature controlled, humidity controlled, and yeah, you have to wear this bunny suit thing they call it at the bottom to do all this stuff. And so a quick description of how you actually make these. It's kind of a complicated process, as you can imagine, but this main technique is what we do over and over again to fabricate these, is that you have your sample or your silicon wafer that you start off with everything, and you put this material called photoresist on it. And this photoresist material is sensitive to light in a particular way, so we put like a mask on it basically, and we can shine a pattern on it. And when we shine this pattern on it, we can do something called develop it, and we're left at the end with our wafer and just the pattern, and then we can do all the different types of metal deposition, create different resistors, our thermometer, TS, all these different things are basically built off this principle that we use a mask and light to create this material out of photoresist, and then we deposit whatever metal we need to do this. For example, this actual TS part here is made of a combination of one layer of moly or molybdenum and then one layer of copper. And then these are the wires basically connecting to our thermometer, and those are also made from molybdenum. And so we had a mask that designed this pattern, and then we deposited these different metals to get this pattern and to actually make the thermometer. And so one thing is, to make these really good detectors, we have to do a couple of things. We can't just fabricate them. We have to do some other considerations. The first consideration that we do is that we have to make our detectors really, really cold. And that's because to get these really sensitive measurements from really far away, you get really small signals, so you have to try to do the best you can to get rid of any noise. And so I have this figure up here that one X-ray changes your thermometer temperature 0.000 to 88 degrees Fahrenheit. And so you don't want you want as little noise as you can. So if you're warm in the room like this, that you're getting a lot of noise and you're not going to be able to see that really, really tiny signal. So I have this table to kind of give a reference, is that things like room temperature is 72 degrees Fahrenheit, your freezer is 0 Fahrenheit, space itself is negative 454 degrees Fahrenheit, and then our cryostat is negative 459.58 degrees Fahrenheit. So really, really cold. And that again helps get these really, really small signals from far away and not get a lot of noise. Otherwise we wouldn't be able to see the signal within the amount of like thermal noise that you get even in space itself. And this picture on the right is something we call a dewar, which is basically how we keep our detectors cold, and it goes on our rocket. And this particular dewar has been on the last 7 rocket flights, but we'll be designing a new one for our next flight. That's in a couple of years. And so the next thing that we have to do to make our thermometers really good is we make them superconductors. So this is kind of a superconductor, maybe is like a common thing people hear about nowadays. It's kind of a cool physics thing that has a lot of applications. I put some of them here, like they make the maglev trains with superconductors. When you get an MRI, they're using superconductors to do the imaging. And then people also want to do like power grid stuff with superconductors. And that's because of some of their properties. These two are the two main properties that people talk about a lot, is that when you cool your superconductor below a critical temperature, which is also normally pretty cold, you get zero resistance. So if you're running like power through a wire that is superconducting, you're not going to lose any energy. That's not like an approximation, that's like you won't lose any energy. So people want to run electrical wires and power lines with superconductors, and you won't have any energy loss, which would be great for a power grid, but hard because right now superconductors have to be really cold. So the energy to keep a superconductor cold is the same. But so some people are researching high temperature superconductors. Anyway, they also expel magnetic fields when they go below this critical temperature. Yeah. But the main reason we use them is because they're a really good thermometer. And so the plot on the left is kind of showing as you cool down a non-superconductor and a superconductor, you kind of get this really, really steep part of the curve for a superconductor, and that's really important for us. The plot on the right kind of does a zoom in of that, and so you can think of this, you're at a high enough temperature on the right over here, and you're a normal metal, and then you're going through this steep transition curve, and then eventually when you're at a low enough temperature, you're becoming a superconductor. And why that matters to us is that we operate our detectors right around here in the middle of this really steep part, and so we're in between kind of a superconductor and a normal metal. And so since it's really steep, if we have this small photon with very little energy hit our detector, we have a very small temperature change. But that means since we're on such a steep curve, we get a really large resistance change. And what we're doing to measure the temperature change is we're measuring the resistance change. So with a small signal, a small temperature change, we'll still get a large enough signal that we can actually make a measurement. So that's why we're using a superconductor here, so we can get a really sensitive thermometer. Basically, when you have a small temperature change, you get a big reading, and you can get really good resolution from that. Yeah. So now I'll talk about, now you have all these pieces, how do we actually collect the data? I'll start talking more about the rocket and the sounding rockets we use. But to start off with, the reason we actually use a sounding rocket at all is because X-rays don't penetrate our atmosphere, which is very good because you're not constantly hit with X-rays, which are not good for you. But all X-ray satellites and telescopes all have to be orbiting Earth. You can't see anything from the ground, which is not like optical. Optical you can see very well from the ground. You can see better from space, but you can see from the ground, which is why we can see anything from the sun. But yeah, so that's why our group does sounding rockets, because we need to get above the atmosphere to get any data. And so I'll talk about, again, I said in 2022 we went to Australia to do a launch. This picture here is a map of Australia, and this point here is where we were at the very top. And then this is a nice little arc of the expected launch, but these little rings are like the different estimated error of where we could have landed the rocket after, I guess. Because we actually we get the rocket after. You can reuse it, so they send a helicopter out and do like a little grid search to find it after. But as I said, we need to be above the Earth's atmosphere, so our rocket goes to above 300 kilometers, which is only slightly below the International Space Station. There's a lot of G-force. We get 30 G-forces with it's spinning very fast, which I'll show a video of. We only get around 5 minutes of data, but we get 30,000 X-ray photons. You can make a nice spectrum, and we do a large field of view, so we like looking at a large portion of the sky to get a lot of counts in a small amount of time. And I guess for reference, I put that the moon is like half a degree in the sky, and our field of view is like 60 degrees, so much larger area in the sky than the moon. And I said, yeah, we reuse the rocket. This is a picture of the launch site in Australia. Over here on the left is actually where we launched. And then this this is the zoom in of over here, which is called they call it the PIF, the Payload Integration Facility, where you're putting all the parts of the rocket together that you have shipped from the US, and testing everything to make sure everything works, and eventually you drive it on the little truck around to where you're going to launch it. And then behind this picture here is something called the blockhouse, where you sit in during launch night and you're like sending all the commands and looking at all the data as it comes in. This is a picture on the left of, over here is kind of the science part of the payload. And here's a helium dewar. So as I said, we have to run our detectors really, really cold. And so the first step in cooling them down to these really low temperatures is to put them in a dewar with liquid helium, which I don't know the Fahrenheit temperatures, but we'll get it down to like 3 Kelvin. And then we do some other processes to get it even colder. But yeah, we have to transfer a lot of cryogenics to get to the starting really cold temperature. This picture on the right is at the bottom of the rocket, or the bottom of the science part of the rocket. Below this is attached the 2 thrusters. And so this part here is called a gate valve, which is basically just the shutter. And so we keep the shutter closed during all of launch and when it comes back down, but when we're collecting data, obviously we open the shutter. The interesting thing though is on the back side of the shutter, or on the inside of the shutter, we have some calibration sources. So basically radiation sources that are emitting X-rays. So when the gate valve is closed or the shutter is closed, we have calibration sources where we have a known energy, and we're hitting our detectors with that constantly, so we can make a little calibration of what our detectors will look like on the ground and in space right before we take actual data. This is a picture of the actual launcher. And so the rocket goes kind of down here, and then it goes to, I forget the angle, but goes to a steeper angle before it gets launched. Here is the little thing that rotates it to raise up the launcher, which they put on. Someone was very funny. And so it rotates and you can see it happy and sad. Here, so this is a video not of our rocket, but of, I guess, someone else's rocket. And so you can see the launch. Basically, I guess someone put a GoPro on their rocket, which I'll have to ask if we can do that for ours. But it's spinning really, really fast because it wants to. You want it to. It'll help stay on target. So it's spinning really, really fast. Which is also how we get to like 30 Gs, more or less. But then once we're taking data, we don't want to be spinning really fast. We want to be basically still. So it has these 2 yo-yos, they call it yo-yo despin, there's a tiny explosion on the rocket once you get to a high enough altitude. And these 2 yo-yos basically are thrown out that are attached to the rocket, and they spin opposite the way you're spinning, and it slows it down almost immediately, which is pretty cool, as you'll see in this video. Okay, and then now I have videos from our rocket launch from 2 years, 2 years ago. They said if it wasn't as cloudy as it was, there was like 2 stages of the rocket, you could have seen the second stage burn up, but it was pretty cloudy. Here's another video of the same launch. Yeah. Okay, that's kind of all I had. Just summary of the talk is that we're trying to study what the universe is made of and see what kind of elements make it up, so we can do kind of careful accounting and study things like galaxies and stars. The way to do that is you can take images, or you can take spectra, which are really powerful to tell you how far things are away from you, and also tell you exactly what elements they are, because each element has a very specific energy and light wavelength that it produces. And again, we use light primarily in astronomy as the messenger to study things, and we can't really go out there and study them ourselves. We have to just see what light comes to us. There's detectors called CCDs, which are the same ones in your phones, that are very good at making images, but can also be used to make spectra. My group uses thermal detectors called TESs, that rely on superconductivity and operating them really, really cold to get really high resolution data. And lastly, we use rockets to do that. And that's it. If anyone has any questions, I'd be happy to answer them.
So if you have a question, I want you to raise your hand and I'll bring the microphone to you so that we can pick that up with a recording. But I'm going to start. Most of our speakers fall into the 2 traditional categories of, you're either a theorist, in which case you don't observe, you use other people's observations, or you're an observer. But you're kind of a third category, you're an observer and you build your own instruments.
Yes.
I'm just curious, when you were applying, or thinking of applying to graduate school for astronomy, did you know then that you wanted to build instruments? Say a little bit about how you came to this place.
Sure, yeah, so I guess it was interesting. In undergrad I studied physics, and my undergrad had an astrophysics track, which I did, which was like 4 courses. But I started off in a condensed matter physics lab, which is like 2D materials, I guess, like graphene a lot, and other types of quantum stuff. But it was very hands-on, so I learned a lot there, but then I wanted to do more astronomy or astrophysics stuff, and then I joined a lab that was radio telescopes and making like small arrays of radio telescopes, like actually making them to be put in Canada. And then I also did some small stuff with like a school-led rover that was going to go to the moon. So I always liked hands-on stuff, and I thought that was more interesting. I didn't want to spend my entire days on a computer, otherwise I would have done computer science. But then, so when I was applying to grad school, I was applying to programs that were like astrophysical instrumentation, so I kind of knew what I was applying for. But actually, when I went to Australia, I hadn't even started grad school yet. That was like the summer before, but my advisor was like, you should come anyway, even though I didn't know anything about anything, so it was kind of like a jump into the deep end of the water and learn everything.
I was just wondering how often you launch these rockets on a regular basis, or?
Yeah, so the previous rockets, probably every 5 years or less, just because they kept the same detectors and everything, they could reuse the rocket basically. Between this last one in 2022 and now, we're basically doing brand new everything, which ideally will also be 5 years, but who's to say? But other groups, so when we went to Australia, ours was the first rocket to launch, but there was 2 other people who were doing sounding rockets, and there's a bunch of other groups that also do sounding rockets, but they typically do like a shorter time scale, like 1 launch every 2 years or something, because they don't have to change as many things.
Because you said 7, you had 7 of them, that'd be 35 years.
Yeah. Yeah.
Hi, so you hold your thermal detector on the lower end of the log curve to try to capture this very small signal from the X-rays. How many sort of shots are you taking per rocket launch where you're moving the shutter back in front of the detector, or are you sort of letting it run and calculating the signal over time, or are you saturating your well, so to speak, or can you give a little more color around that part of the process?
Yeah, sure. We can go back to that too. So the shutter here, the shutter stays open the entire time. The shutter is only closed during launch and everything to keep everything safe and everything in new calibration. But as you're saying here, yeah, a lot of times one problem that you have is that if you get a photon that's too high energy, you'll completely saturate and you're completely off the steep part of the curve. And so we do get some saturating events like cosmic rays or high energy electrons, and that can basically just end up getting dead time on your detector, so you can't get any data then, but that's a small portion. The other thing that's really important to consider here is you have the temperature here and then you get a hit, but how fast do you decay back to your base temperature? And so there's kind of a game of like, do you want to be really, really fast? There's other reasons why you don't want to be fast, and there's reasons, obviously, if you're too slow and you get 2 hits at the same time, it'll be really confusing. So there's kind of like a middle ground of how fast you cool down to the temperature that you started at. And so, yeah, there's some other things with like actually making the detectors, the different thicknesses of the different metals and whatnot dictate all of this. So, but yeah, you want to be around here and fast enough that you don't get too many counts or too many X-ray hits where you're like just bombarded all the time and you're not able to cool down fast enough, but you also don't want to be too fast. And yeah, we do get some saturating events, but not too much that it's awful.
Yes, actually I have 2 questions. The first is, I noticed the dewar was apparently made of metal, and I'm wondering, I assume the metal does not interfere with the X-rays, as many metals do. What metal is it?
That's a good question. I think it might be aluminum, but I'm not sure. But there's also, so that's like the outside dewar, which probably there's like a lot of insulation inside, and then there's also, you have the liquid helium in kind of like a container inside, yeah, and then you have like a couple more layers, and like there's a lot of thermal isolation, so we have like each stage is a different temperature, so we have like a room temperature stage where all the metal and everything is room temperature, and then we have like a 50 Kelvin stage, and then a 3 Kelvin stage, and then a 50 millikelvin stage. So there's a lot of thermal isolation, and I guess some also electrical isolation. But I think aluminum, but I'm not 100% sure.
But clearly the X-rays do get through, so.
Yeah.
The second question is, what do you actually do with the data? Are you looking at the energy spectrum of the X-rays, or?
Yeah, so ours, we're doing energy spectrum for the X-rays. Our group particularly looks at the local galaxy to get an energy spectrum and figure out particularly what type of supernovae have produced. We're in something called the local hot bubble. It's a really hot plasma of gas, but people would want to know if it's a lot of type 2 supernovae, type 1 supernovae, other factors like other X-ray factors like something called active galactic nuclei, all these other contributing things that we can learn from the energy spectrum of the electrons or the X-rays and what types of elements we're seeing.
I wasn't sure if I missed it or not, but why did you end up going to Australia? There are other places you can launch from. What was the magic of Australia other than it's a wonderful place to visit?
Yeah, it was a great place to visit. So typically when we launch our rockets, we typically go to White Sands Missile Range, which is in New Mexico. Much easier because it's much closer and you don't have to fly all your equipment across the sea and everything. But we went to Australia because this particular launch 2 years ago, we were looking at something you could only see from the southern hemisphere. And so we went to Australia. Yeah.
What is the process for metal deposition in the lab for making the thermal sensors?
Yeah. So there's a couple different processes. There's one called evaporation and then one called sputtering, but mostly we use the evaporation technique, which is basically you have a crucible of the metal and you're hitting it with an electron beam and you're heating it enough that it starts to evaporate, and then you have your sample kind of in direct line of sight of the evaporation, and then you're coating your sample with whatever metal you're evaporating. And then since you've patterned it with this photoresist, you can kind of basically do this, remove some of the photoresist, and then you're left with just the metal pattern.
Anybody else?
I'm just curious where the deposition lab is located. Is it in the School of Engineering, or
Yeah.
whose facilities do you use?
Yeah, the clean room facility, which has most of the deposition material or equipment and all the other equipment, is in the engineering, or there's some also in the material science.
All right, well, if there's no further questions, I'd just like to say, God, this has got to be the neatest way to do observing. I just start chuckling every time I see a rocket like that take off. So, and not to mention dealing with all the cool cryogenics and things and building your own equipment. As a chemist sometimes like building their own instruments and things too. So it's God, it must be a lot of fun.
Yeah.
So,
I think your microphone is on.
oh, it's on mute. All right. Yeah, it was. That's much better. So, as I was saying, on behalf of Madison Astronomical Society, I would like to present you with a little
Thank you.
token of our esteem, and it works with any beverage you would care to enjoy.
Thank you.
And I'd also like to congratulate you on a really fun and fascinating career. And thank you so much for being here today.
Yeah, thank you.
All right, so that will conclude this month's meeting of the Madison Astronomical